Do a quick video to fix causality in space-time. Uh, there are examples where you can see that you can rearrange the order of events that occur, where uh, you could think that lightning strikes, what a left pole before it strikes the right pole, where someone else thinks they strike at the same time, and somebody else thinks that they strike the opposite order. So what we want to do is fix this, and it's with basically time and distance and all these things. They are not invariant in special relativity. They change, and so we can't agree on the ordering of events and the timing of events and everything like that. And so that kind of throws science for a loop, because if we can't agree on that, maybe we can't agree on the order in which things happened, and we kind of break causality and break science. So what we're going to do here is we're going to fix science. We're going to fix causality, and we're going to do it with something called the space-time interval. Okay? And this should be a pretty short, quick video, but basically this space-time interval, this is invariant between inertial frames. So this is invariant between inertial frames. And so what that means is no matter what your frame of reference is, no matter what inertial frame you're in, no matter how you're measuring distances and times, everybody that measures the space-time interval between events will get the exact same number. So this is something we can actually agree on, and it looks like this. This is the space-time interval, delta s squared equals c delta t squared minus delta x squared. Now this may look a little bit like to you like from regular geometry, where you had c squared equals a squared plus b squared, and it is similar to that. This is essentially the metric for regular old Cartesian or Euclidean geometry, right, where everything can go in circular paths and all that stuff. Whereas if you look at this one and you're pretty good at recognizing your math and that kind of stuff, this is actually the form of something that is hyperbolic, that form these hyperbola, and it's a hyperbolic type space, not this space anymore, not this rectangular circular kind of space that we get from that. Like if we went around and kept c constant and we drew out all the possible a's and b's, we'd draw out a circle. Well, here, if you keep delta s squared constant and you do all the possible ct squareds and the delta x squareds, you draw a hyperbola. So, and we'll talk more about this, but these hyperbola, they go kind of like this. So they go like that, and then these would kind of curve up. Well, oops, they shouldn't be touching there like that. This wouldn't actually touch. They'd just get really close together, and then the next one would go up and get real close to it, and they get closer and closer. And so this is what hyperbolic would draw out, rather than the kind of circular thing that would be drawn out. And so that's a space-time interval. And this will make a little more sense in the next video, where we actually talk about the space that this is contained into, Minkowski space or space-time diagrams, and it'll be a little better in there. But essentially, everybody that measures this is going to look at this. It's very similar to regular old a squared plus b squared, but you can look at this and you can calculate it. And again, in the next video, this will make a little more sense. But if this is a positive number, if it's positive, it means events might be linked. It means that the first event could be linked to the second event, and they might actually be linked. If it's negative, they're definitely not linked. Okay? They're definitely not linked. And that's pretty much everything there is about this. There'll be more of it in the next video. This was just a little quick introduction.